Welcome, everybody. Thanks for coming. I'm Brian Cavalier. I'm going to be presenting with Craig Walls on the topic of efficient client communication with differential synchronization and JSON Patch. And we win the prize for longest talk title. We were in close competition with Fabrice, who presented earlier this morning, but I think we pulled it out in the end. So I want to start out with a question, maybe a controversial question. What's wrong with REST? Good answer. Good answer. That's what I think too. I think that nothing's wrong with REST. REST is awesome. Here's another question. What's the problem with how we typically use REST in practice? And before we answer that, I want to do a show of hands. So how many of you write REST APIs? Raise your hand. Okay, great. All right, next question. Of those of you who write REST APIs, how many of you are serving up data to mobile clients, either native or a web browser on an iOS or Android device? Okay, great. Pretty high percentage. How many of you batch requests, REST puts, puts, deletes, whatever, using HTTP patch? Raise your hand. Okay, one hand went up. Okay, yeah, that's really interesting. We're going to come back to that question in just a second, but I want to give you the agenda. We're going to talk about, as you probably guessed, why are we doing what we're doing? Why are we talking about differential synchronization in JSON Patch? And it has to do with the question I just asked. And then we're going to talk a little bit about these new technologies that we're working on. So let's go back to that question. What is the problem with how we typically use REST in practice today? And based on the number of hands that went up, I'm guessing that most people, the way you use REST is that you typically do one request per operation type per entity type. And so what I mean is you have, you want to create 2 new entities, you do 2 posts, right? You want to update 3 entities, you do 3 puts. You want to delete an entity, you do 1 delete. And that means 6 HTTP requests, okay? Now on a desktop web browser, any sort of desktop client, that's not really a problem, right? We don't really think about it. Because networks are fast, latency is low, it's easy to plug in a laptop, use it on wall power instead of battery, or we're using a desktop that's always plugged in, we don't have to think about battery. And we're not on a data plan, right? We're probably using Wi-Fi. But in this new world, right, a lot of you raised your hands. You're serving up data to mobile clients, right? People who are not plugged into the wall. People who are using wireless networks, LTE, right? Data plans, paying for data. These things have radios that need to be powered up and powered down. That drains battery life. It turns out even in LTE, even though the data transmission speed is super fast, sometimes better than Wi-Fi, the connection latency is the issue, right? Creating a connection is the expensive part of the wireless network, not transmitting data. And oftentimes, we don't fully exploit the return payload of these puts and posts and deletes that we're doing, right? There's an opportunity there, right? We could learn something about what happened on the server if the server would just tell us in that response. So the way we apply REST really leaves open some opportunities for improvements, especially when we're talking about mobile. So what we wanted to do is think about, in this world and in the context of Spring, how could we make that data transfer more efficient? Why do we have to do one request per operation, per entity type? Can we do better? How can we more efficiently make use of the mobile radio? We don't want to power it up and down for every request we make. How can we use the network more efficiently, right? Connection latency is the problem. Creating more connections takes more time. And how can we save people's batteries? We also wondered, what is our story for WebSocket? How can we take advantage of that in mobiles? How can we do more? And how can we keep multiple clients in sync with a server? How can we support offline mode? These are all concerns that we have to worry about, people walking around with multiple devices. So essentially the question for us kind of came down to this. How can we get data from a Spring backend all the way to the pixels of any device very efficiently? So when we started thinking about this back in 2013, we came up with several ideas, and we did some research, and we were sort of generally looking at how can we make the landscape of client-side development better for Spring developers. And we came up with several ideas. One of those you saw presented yesterday by John Han, Rave.js. What is the developer experience for someone developing client-side applications? And making that more like Spring Boot with Rave.js has been one of our answers. And then when we were looking at the communication piece of that, we found this algorithm called Differential Synchronization. And I'm going to tell you sort of an overview of the algorithm, and then we're going to get into the specifics, show some demos, but I want to explain it first, talk through it, a little bit of the history of it, how it works, and then we'll dive in and crack it open. In the most simple way I can explain it is that it's an algorithm for keeping n copies of some document in sync. And it's a very generic algorithm. It's based on the concepts of diff and patch, right, which we're all familiar with. If you use a version control system, you're familiar with diff and patch. So originally, the algorithm was applied to text documents, right? Text, diff, and patch is a solved problem, right? We do it all the time. But it turns out the algorithm can be applied to any kind of document. And you can imagine, right, in a web browser, the DOM is a document, right? A JSON object is a document. They're structured documents, but they're still documents. So if we could write diff and patch for those kinds of things, we could apply this algorithm. It also has some really interesting properties just by its very nature. Because it's based on diff and patch, it transfers only differences, meaning payloads are small, okay, very efficient. It's also symmetrical algorithm. Even though we're going to be talking about it here in the context of client-server, which we don't normally think of as symmetrical or peers, the algorithm itself can be applied to peer-to-peer, server-to-server, client-server, many use cases for the algorithm. And it turns out that it's the same at every node, so you don't have to have special code on one node and special code on the other node. You can run the same algorithm at each node. It also lends itself to being easily recoverable. And why that's important is on a mobile device, right, you may not have the network for a minute, 2 minutes, 10 minutes, 5 hours. And the algorithm sort of naturally recovers from those situations. And I have to give credit to the author. It was published originally in 2009. There's a link here. The paper is extremely approachable. It's actually a pretty easy read. I encourage you to go read it. There's not a lot of math. He explains it very well. So now that we sort of have the history of it, what does differential synchronization look like? Here's a simple, fairly simple picture. of how it works, and I'll walk you through it. We have two documents, one on the left, one on the right, that we want to keep in sync. And let's just assume that the two documents start out the same, right? Maybe they're empty. But on either side, users may be changing the document. A good mental model to start with here is collaborative text editors, right? And that's where this algorithm has been applied in the past, right? You got one person on machine A, machine B. They're both editing the same document collaboratively. So user A may change the document on the right. At some point, the algorithm does a diff between that document and what's called a shadow copy. And the shadow copy starts out the same as the two documents. So really, we have three copies of the data in sync. So the user changes the document on the right. The shadow hasn't changed. You do a diff between those two that generates a patch file. You send the patch to the other party. The other party patches both the shadow and the document, which may have changed. The user may be editing it. Right? And the algorithm continues. The user on the left, their text editor, does a diff between the document, their copy of the document, which may have changed, and the shadow that generates a patch file that's sent back to the first user's text editor. And the algorithm continues in a loop. Right? It's not willy-nilly, back and forth, crossing patches. It's a loop. Very important. Another important thing, let's see if you can spot it. There's a problem with this picture if you start to think about client-server. Anybody spot the problem with this for client-server? Right. How do you have a single shared shadow copy when what's between these two documents is a network? Right? Where does that thing live? So in the paper, he presents it this way because it's sort of the easiest way to get your head around it, and it was for me. And the author goes on to present a sort of more sophisticated version of the algorithm. It's not much more sophisticated, but it solves the problem of this single shared copy. So each side maintains a shadow copy. And really, the algorithm from there works the same way. The user on one side does a diff between their shadow and their document. They're changing the document. That generates a patch. It's sent to the other side. The other user applies the patch to both the shadow and the document. Document may have changed, does a diff, sends the patch back to the first party. And again, just continues in a loop. And in the middle here could be a network. So that's the overview. And just in summary, it's a cooperative synchronization loop. It can be distributed, or it can be local. And it uses diff and patch. And so we can apply this algorithm to anything that we can write diff and patch for. Now, the other thing that we found when we were investigating this space of making client-server communication more efficient was that obviously we needed a patching format if we were going to use this algorithm, Differential Sync. And it turned out that there is an RFC for a format called JSON Patch. Has anybody heard of this? Raise your hand if you've heard of JSON Patch. Okay, a few hands went up. Okay, cool. It's not official yet, but it has gone through like 10 or 11 revisions. So it's a pretty solid RFC. And it defines a patching format for JSON documents, and the patches themselves are JSON. Okay, got that? It's JSON-formatted patches that patch JSON documents. So here is a patch format for structured documents, right? Trees. You can patch anything that's a tree. It might contain lists. This format can represent patches. Because it's JSON, It's suitable for sending over HTTP patch. It's suitable for sending over stomp, whatever transport you want. And the RFC defines a set of patching operations, adding, removing, replacing values. It defines the patch format itself. It actually defines the patching algorithm, which is quite simple. And it defines a MIME type for transmitting JSON patch over whatever your transmission mechanism is. So HTTP, for example, you can transmit it with this MIME type, application/JSON patch plus JSON. That allows it to coexist with other handlers. So if you're writing a Spring app and you're routing based on content type, and you have an HTTP patch endpoint already, you can route specifically JSON patch by using this content type. One snag, however, is that the RFC does not define a diff algorithm. Okay? It doesn't say, how do you actually get one of these patches? That's sort of up to you. But there's kind of this sensible requirement, right? If you have two JSON documents, A and B, you diff them, creating a patch file, and then you patch A with that patch file that you just generated, you better get B. Here's a simple example of what it looks like. So at the top, I've got a very simple bit of JSON, right? An array. It's got 3 objects in it, value A, value B, and value C. And in the middle is a simple, very small JSON patch. And it has 2 operations. The first one is an add operation, and the second one is a remove operation. And the first one says, add at index 3 a new object, value D. And the second operation says, remove the value at index 1. And so when we take the array, we apply the patch, we end up with a new array with D added and B removed. Okay, here's another example. You can patch anything that's JSON, right? In the previous example, we patched an array. Here we're patching an object. We can reach into the object. The path can be a deep path. Okay, we can reach into this object, which you can imagine is some sort of data entity on your server. We can reach in and just change one field, changing the occupation. So there's some interesting things about this sort of deceptively simple format. And one is that, as you saw in the examples, right, we've got this operation that we're not representing as an HTTP verb anymore. It's actually in the patch. It's in the payload. So what that enables is for us to batch multiple types of operations into a single patch, right? We can create 2 entities, update 3 of them, and delete 1 of them from the same collection in a single request by sending a single atomic patch, which contains all of those operations, over HTTP patch to the server and having the server apply it. So instead of 6 requests, we can do it in 1. It also moves, if we look back at this again, specifically this one, it moves the part of what I'm going to call the identifier, right? In the REST world, we typically think of resources based at a URI. The JSON patch has this path property, which allows you to specify, where in this thing that you're patching, where does this patch get applied? Where does this operation get applied? So we're moving some of the information about the resource and where we're going to be updating it into the payload. And this has some really interesting potential as well. This is an area that still needs some thought and research, but there is some serious potential here. So imagine your server, right? You have, who writes an application that has 1 data entity, right? No one, right? You have many data entities, right? And so when you do REST in the typical way that we do it, the number of requests is number of entity types times number of operation types, right? You get this multiplicative number of requests. JSON Patch, by putting the identifier inside the payload, could potentially allow you to reference multiple types of entities in one patch. So if you've got a resource that is person, and a resource that is to-dos, and a resource that is meetings, right? And you want to change 2 of the person entities, 3 of the to-do entities, and 10 of the meeting entities, you can actually do that in a single patch, which means a single request. The other interesting thing you get from being able to do that and combine those patches, combine those operations into a patch, is that the RFC specifically states that the patches have to be applied atomically. So if you were doing traditional REST, right, you've got to spread these operations out across, or we tend to spread these operations out across multiple requests, meaning it's very difficult to do them in a single transaction. But if we can do them in a single request, we can do them in a single transaction. So we can do cross-entity transactions, potentially, using this kind of approach. So here's a couple examples. We've already talked about this, but this is an example in sort of typical REST style, right? Creating a to-do, updating a to-do. Maybe we're using HTTP patch in sort of a more traditional way to do a partial update to a to-do, and then we're deleting a to-do, right? 4 requests. So if we do that in JSON patch over HTTP patch, we can do a single request, and we can put that same information into the patch itself. So 1 request to do all 4 of those operations. And again, the potential is here to do something like this, where we've got multiple entity types, right? Meetings, people, to-dos. Instead of doing 4 requests to do this, maybe this set of related operations, we can do it in a single request. So the goal here really, or the benefits really, is reducing the payload size by transferring only deltas and reducing the number of requests, which translates on mobiles into reduced latency. All right, so let's see a demo. I've got a small Spring app here on the back end. And as you can probably guess, if you can read my font, don't worry, you don't need to read the terminal. This is a very simple to-dos app, because everybody writes to-dos apps, although I just saw on Twitter that word count or character count or word count is the new hello world. Maybe I should write a word count app. All right, so, oh, come on, Chrome. Anybody else fight with Chrome caching recently? All right, so we've got this to-dos app, right? Really simple stuff. I can check these off and reload, right? It sticks. I can delete them. I can add new ones. Simple stuff. All right. Let's look at the network panel. All right. So if I add a new to-do, let's watch the network panel. Okay, nothing really exciting there, kind of what we expect, right? We created one to-do, we got 1 request. It was a patch request, though. That's different. Let's look at that. Okay, so the payload was a JSON patch, what we'd expect. Let's do something more interesting here. Let's add a bunch of to-dos. I'm going to make this smaller because more will fit on the screen if I do that. bunch of to-dos in here. That's not enough. I do 2 ones. Let's get rid of that. What? That's interesting. Haven't seen that one before. Okay, so we've got a bunch of to-dos that have very strange-looking check marks. Like, I don't know, what, 18, 19, 20 of them, something like that. Okay, I'm going to crack open the network panel again so you can see it. This button up here, which should be a check mark, is a check all button, right? Complete all my to-dos, I'm done. So what we would expect in traditional REST is when I click this button, for all the check marks to turn green and to get, what, 20-some odd put requests. Right, let's see what happens. Hey, look at that. 1 HTTP patch connection. Let's look at the payload. And the payload is a patch. There's double the number of items in here. We're sending sort of extra safe patches right now. One of the patch operations that JSON Patch defines is called test. That allows you to test the target thing that you're patching to make sure you're patching what you think you're patching, right? Does it have the value I think it has? And that allows you to fail patches atomically, right? If any part of this patch fails, which might be a test, fail the entire thing. So we're sending right now sort of extra safe patches. So the payload is a little larger, but still we did it in a single request. And I could archive them all again. I get a single request. Yeah, question? Yeah, yeah. That's just how we set up. There's nothing special about that URI. It's just what we happen to use for this demo. That endpoint is going to take on more meaning when I do the next demo. Foreshadowing. Oh, question?
So the test is kind of like optimistic locking. Could you use version number or something like that?
Yeah. Let me repeat the question. The question was, it looked like we're using optimistic locking. Could we use a version number to prevent collisions or old data, trying to patch old data? That's a great question. I'm going to cover that in a little bit more detail later. Just a hint right now, it turns out that when you have a system based on diff and patch, if you think about how you use Git, right? Everybody in here use Git, right? Do you lock files in Git when you use Git? No. Right? What do? You just go for it, right? You just push your changes. And if they don't work, what happens? The whole patch fails. That sounds familiar. So you can actually apply a lot of the techniques that are used in version control once you have a system that's based on diff and patch. And I'm going to talk about that in more detail. All right, let's go back to the slides. I want to introduce, we've been working on the client side and server side of all of this. We have created a library that implements the JSON Patch standard in JavaScript for the client side. And it also implements the diffing algorithm. So this is sort of a full-service library for doing the kinds of things that I just showed. It doesn't do XHR, it doesn't do the network transport, but you can use your favorite library. If you use Cujo.js, you can use REST.js. You can use whatever you normally use to send this over HTTP patch. The library can diff arbitrary graphs of JSON or JavaScript objects, arbitrarily deep objects containing arrays, containing objects containing arrays. It can also patch arbitrary JSON and JavaScript object graphs. And it has some pretty interesting advanced features that we're exploring. This stuff is definitely experimental, but we have it working in this library. once you are dealing with diff and patch, if you think about, again, Git is a good mental model here, right? There are some pretty interesting things that you can think about starting to do once you can deal with patches. Talk more about that later, and that'll go to your question too. This is just a quick code sample of using jiff. You just require it. It's got some useful methods on it. It's got this clone method that actually lets you make a copy of your data. It does a deep copy. And then you can let your program change some data, let the user change the data, create a diff, send that diff to your server over HTTP patch in just a few lines of code. Okay, so that's an overview of differential sync and JSON patch. And by now, you probably guessed where this is going. There's an obvious fit here, right? We needed a patching format, and we got it from JSON patch. So what would happen if we put these two things together? So going back to our picture of differential sync, right? Got this loop, right? We know that we separated that shared shadow in order to move this onto a client and a server. So what would that look like? Well, we'd start transmitting patches using JSON patch. And then we draw a line in here and say, okay, on one side of this line, we've got our Spring-based backend. And on the other side, we've got some sort of client, right? I'm going to be demoing primarily JavaScript clients running in a web browser, but this could just as easily be applied to a native iOS application, native Android application, Windows Phone, whatever clients you need to support. The algorithm is generic and can be implemented for those platforms. So again, we're taking structured data on the server, using diff to generate patches, sending them to the client. The client can do the same thing, produce patches, send them to the server. So what would that look like? Let's do another demo. So the demo I showed you last time was a to-dos application. I'm going to use the same application. But this is a slightly different version. You can probably guess what it's going to do. All right. I'm going to throw in a twist. All right. Everybody see both of those? Oh, that's big. All right, so we got three browser windows open here. Let's see what happens. Oh, hey, look at that. Did I catch that? So what's going on here? Let's add some over here. I'll use Chrome's debugger. Oh, come on. Something failed. Error. Man, it's not a good day for demos. Everybody's demos are breaking. Wow. Let's restart. Start over. It was going so well. But what you saw was, right, when I checked off in one browser, the other two browsers updated. And so each browser window and the Spring server are running the differential synchronization algorithm. And so what's happening is when I make a change in one client, I'll do it over here so you can see all three. That client is producing a patch, right, in its turn of the synchronization loop. A patch is getting sent to the server. The server is then on the next turn of the other two clients' synchronization loop, doing a diff, sending a similar patch back up to the other clients. So each client is running the loop, right, against their own shadow copy. So changes can propagate back to the server, and the next turn of the loop of another client, they get updated. All right, let me go back to slides. So that's pretty cool. That's not something we think normally, right, over HTTP is possible, but it is. So I'm going to let Craig Walls come up and tell you a little bit, open up that demo, pull back the curtain, let you know how that's working on the Spring side of things.
All right, so it's been said already at least a couple of times this week. If it's not a good demo if it doesn't break. So I think we had a good demo. What do you think? All right. So here's essentially what's happening. We've already talked about, Brian already mentioned that when JSON Patch was originally intended as this patching, this patch definition that you could apply to a JSON document, which is what's shown here. Turns out, though, that a JSON document is just a tree. It's just a graph of information. And if you step back from it a little bit, you think, well, you could apply it to other types of things, not just JSON documents. I mean, you could apply it to perhaps a DOM. You could apply it to, or another type of object that or object graph we might deal with frequently. You might apply it to your Java objects, because all they are is just a graph anyway. And so, as I approached this problem, building this on the server side, I faced an issue. The first time I tried to do it, I was successful. It worked. But it didn't feel right. And what I did was I fetched the data from the database. So it's now in Java object form. And I did the most straightforward thing that just seemed like the most natural thing to do. Convert those Java objects using like Jackson, convert those into a JSON node. And then let's apply the JSON patch to it. And now that the JSON node has been patched, the JSON document has been patched, let's convert it back into a Java object and save it. Well, that seemed like a good idea, and it did work. It presented some issues, some challenges, but gosh darn, I couldn't feel good about it because there's a lot of moving around, going from Java object to JSON node and back. And so I thought to myself, it would be really cool, and actually it's not entirely my brilliant idea. We had some discussions among the team, and some of the other guys and some of the other teams chimed in, and they said, hey, wouldn't it be cool if you could just skip that conversion back and forth between Java object and JSON node, and just go ahead and just apply a patch to the Java object directly? Because after all, it is just a graph of data. It is just a tree of data, just like JSON is, just like a DOM is, same thing. So I thought, cool, yeah, I can do that. And so I set off to do that. And it was really, interesting experience because I said to myself, well, how do I do that? Because the biggest problem is, how do I interpret that path, that /0/complete or /1? How do I interpret that path in such a way that I can apply it to whatever Java object graph I'm dealing with? And I honestly, I said, I just didn't know how. I had no idea how I'm going to pull this off. I know it's been done before, and it smells a little bit like what we've been doing for years with expression languages like Ognal or even the Spring expression language. And I said, okay, let me draw some inspiration from those guys. Let me go look at their source code and see how they do this. And so I went to the Spring expression language source code, looked it over, tried to see how they kind of interpreted the expressions against an object graph. And that lasted all of about 5 minutes before I said, wait a minute, SpEL does this pretty good already anyway. Turns out SpEL is also a very expressive expression language. It has a lot of power in it, a lot more power than I would ever need in one of these paths. So it turns out I could easily translate one of these paths to a SpEL expression. And so that's what I ended up doing. And it turned out to be very simple. So in the path, if you see /0, well, that becomes SpEL square bracket 0. If you see /complete, well, that just becomes .complete. If you see /1/description, it gets more interesting. It's square bracket 1 .description. And the more interesting one, I had to kind of bake up an example just to show you that it would still work if it got more interesting. /client/3/address/zip becomes .clients bracket 3 .address.zip. I tried that, and of course, a few unit tests later, I had a pretty decent conversion algorithm written to convert it. It's just basically a bunch of string replaces. And then let me apply that SpEL to the objects that I'm dealing with, and I was pleased to say that it just worked. That wasn't all the problem, though. That was a big part of the problem. That's the part I was most worried about. But it did work, and I was like, this is awesome. I can actually apply a patch now to Java objects. Now the question is, now that I know how to apply a JSON patch to Java objects without converting back and forth to JSON node, how do I apply the differential sync algorithm? And so that's what I started to build into this project that we're currently calling Spring Sync. Now, I'll talk a little bit about where that might head here in a bit, but as I started applying this and applying JSON Patch to Java, I started asking myself some serious questions, like how do you deal with removing or moving a property? If this was a JSON document, and the JSON document had a property in it on one area, and I issued a JSON patch with a remove operation. Well, that makes sense. You can just remove that property. Java, not so much. You can't just go take a property off of a Java object. We're not Ruby or Groovy or anything cool like that. We just can't make things go away. Likewise, you can't really move a property. What does that mean? You can't really do that. So that was one challenge. When you say remove, you could interpret that as set it to null. Is that what you really mean? I don't know. But that's actually how we're doing it now. How do you move a list from one index to another? If you're dealing with a list of items, how do you take something from here and move it to here? Well, it's pretty simple. Actually, you just take it from here and move it to here, but wait a minute. How did that thing end up in that order anyway? It's probably a database query at some point that produced that, and that database query probably ordered it that way, and if we were to move it, fantastic, but next time we go fetch it, it's going to be back in the original order, so it doesn't make that much sense to move it, unless, of course, the ordering somehow was, and the indexing was somehow based on some key in the database where we apply ordering, so we might have to do something special in the database itself to interpret the ordering. Right now, we sort of conveniently ignore the ordering. When we get a move, it really means nothing to us as far as a list is concerned. It's more or less a no-op. How do you add a list? How do you add an item to a list at a specific index? Yeah, so what? I can add it at the first item, I can add it as the 5th item, I can add it as the 100th item, but ultimately, again, that resource is defined by the database query that produced it. And that database query, when you go fetch that same list resource later on, may have it in a different order. So, yeah, I can add stuff, but I can't guarantee it's going to be added at the same location. How do you avoid saving the entire list? Let's just say I added one item. I'll go fetch a list from the database. I add the one item. Or maybe I changed a single item. I just changed the property on a single item in that list. How do I avoid saving that whole darn list just because I changed a single property in one of the items? I have to sort of know what changed. I have to sort of keep track as part of this algorithm of which item changed, so I only saved that item. So that became an interesting problem. Originally, I was saving everything and just hoping for the best, but that was a little heavy-handed. Right now, I actually have to keep track of what has changed. How do you delete an item? That's not that hard either. It's pretty easy to remove something from a list, but it's kind of like the save question. If I were to go save that list as a whole, simply saving the list after removing an item does not remove the item. It just saves the stuff in the list. The item's still there and will come back the next time it's queried for. So that was an interesting problem. And one of the things that, as Brian was talking, it occurred to me that I hadn't even thought about when I put this slide together is, along the way, I'm going to have to be making these shadow copies. I'm going to have, at least in the initial one, if I don't have a shadow copy at the beginning of all this, I have to make one from what the data looks like when it's first retrieved. How do I make a copy of a list? Think about it a second. If I make a shadow copy from an original, and all I did is simply say shadow copy equal original, that's not going to work. Because now, anytime I change the original, the shadow is going to immediately be changed with it, when I really need to kind of keep it separate for the moment so I can produce those diffs. So I had to come up with a deep copy, and in Java, deep copies are not trivial. So I had to deal with that. And then, here's another one we haven't even begun to address yet. But what if you go to remove an item, and that item really was only intended for a particular view? Maybe this is a list of data that you're presenting to a specific user on a specific client, and that client instructs you to delete that item, meaning don't let this user see it anymore, but that item still is valid and exists for the purpose of maybe other users. How do you deal with that? Likewise, how do you avoid going too deep and start removing things or changing properties on things that are deeper than the actual resource that you're working with? Because it's entirely possible you could fetch an object that in the database references another object in a different table, which references something else in a different table. You want to kind of maybe set some boundaries on that and say you can only change what was part of the original item. You can't necessarily dig deeper. Or maybe you do allow it. And again, we've just started talking about some of these problems. So this is still a work in progress, but these are some of the challenges that we have to deal with when we come up with this. But what we've come up with is, again, it's a little project that currently is called Spring Sync, just so we could have a name for it, just so you could start looking at it and playing with it. We've also begun some discussions and talked about what we could do to maybe merge it in and make it just support it if you're using Spring Data REST. So that there's discussion underway to make that happen. How are you going to do it if you're not using Spring Data REST? Using Spring MVC. But currently we do have this project, it's called Spring Sync, and here's how you can find the source code in GitHub. So feel free to clone that, try it out, tell me what I'm doing wrong, because I'm certain I'm screwing something up, so please let me know. Pull requests are certainly welcome. And here's how you can get the Maven Gradle coordinates so you can actually build it. I'll leave that up for a second or two. But what it does include is it includes a JSON Patch library. Now, there are a couple of JSON Patch libraries already out there in the open source community, and they're great. They're the ones I used originally when I was applying a patch against the JSON node, and they worked fantastic. They don't lend themselves very well to applying a JSON patch to a Java object graph. So this particular JSON Patch library assumes you're working with a Java object graph, because that's what we wanted to do. In theory, I suppose at some point, if we wanted to grow this, we could also take a JSON node and apply it to that, but right now it does not work that way. It will only work with Java objects. So it includes a very basic JSON Patch library, but along with that, it includes a diff sync library right next to it. And the diff sync library, among other things, uses the JSON Patch to apply the algorithm that Brian talked about to a Java object graph. It deals with the shadow, it deals with producing the diffs, and built on top of all that is a diff sync controller. So it's a Spring MVC controller that reacts to HTTP patch requests, assuming that the content type is application/JSON-patch plus JSON. Assuming that's true, it'll respond to those by applying the patch that it was given, saving it as necessary, producing a diff from its shadow copy, and then returning that diff in the response, thus closing the server-side piece of the loop, which is pretty much what that says. And then just to make it simple to work with, and this is more for me than anything, but certainly everyone here using this and trying it out can benefit from it. I got tired of configuring all this stuff when I was playing with it, so I gave it good old-fashioned Spring enable configuration so that I could easily configure this and enable it. So just to give you a taste of what that enable configuration looks like, That's it right there. That's every bit of the configuration necessary for the to-dos app that Brian is running. It's just a configuration class. It has enabled differential synchronization. And to configure the finer points of that, it extends diffsync configurer adapter. All it does in this case is override the add persistence callback. What this is and it may or may not survive long term, especially as we move into Spring Data REST, but right now it gives some hook to the database. I'm not going to assume anything about your database. I'm not going to assume that you're even using a database for that matter, but if you are using a database, I'm not going to assume that it's a relational database or a document database. I'm not going to assume that I know what the table structure looks like. What I'm going to do is give you the opportunity to tell me how, when it's time to save this resource, how do I do that? And so you implement the persistence callback. In this case, I'm using one called JPA persistence callback, which is kind of a default implementation that assumes some basic JPA operations. And then it leaves, of course, the mapping to the database up to JPA. But you tell me how we're going to deal with your database, how you're going to save things, how we're going to fetch things, how we're going to delete things. And then when it's time to delete something, the differential synchronization will call that. When it's time to save something, the differential synchronization algorithm will call into that. And that's it. I added a persistence callback, and based on the type of that persistence callback, in this case it's a to-do, whenever I get a patch for a to-do, this guy's going to get the job to deal with saving that. And that's all the configuration you need, and it'll make it happen. So with that, I'm going to let Brian tell you about what happens on the client side with regard to differential sync.
All right, so we're going to close the loop now. We've seen how the server works. The client side has an extra interesting piece that you can probably see on this diagram that we haven't really talked much about before. But in those demos, we were applying the same algorithm, the same differential synchronization loop to keep the user interface in sync with data that JavaScript was manipulating. So there was actually data flowing from the Spring server via differential synchronization over the network. That was updating plain old JavaScript arrays and objects in my JavaScript code that was implementing that to-dos app. And that's all the code I wrote. I didn't touch the DOM. The DOM is being updated automatically using the same algorithm, but the local version of it. Remember the shared shadow copy? It's using that version of the algorithm to keep those in sync. And all of those turns of the synchronization loop are using JSON Patch. So we're differencing the DOM and producing JSON Patch, which is patching JavaScript objects. And we're differencing JavaScript objects to produce patches that are sent to a Spring server that are used to update Java objects, which in turn produce JSON patches all the way back up to the top. So again, our goal was synchronize data from a Spring backend all the way to the pixels. And we're almost there. We have this working. It's pretty cool stuff. We're definitely going to be evolving it, as Craig said. The library that we're using to implement differential synchronization on top of JSON Patch in the clients that you're seeing here, I'm going to call it an incubator module. It's not publicly available yet. We hope to have that publicly available very soon. But it is based on the library that I mentioned earlier, which is released, jiff.js. There's another interesting aspect of this algorithm that I want to point out now that we've talked through both sides of it. It gives you this extra control knob, right? This middle bullet. You know, when we do typical REST in practice, we tend to, whenever the data changes, whenever the user makes a change, send the data right then, right? So in a way, the user is in control of our network resource. this gives us this extra control knob, right? We can, as developers, control this loop. We can let the user change the data at a very fast rate, and we can wait. And then at some point, we can create a patch. We can run the diff algorithm and create a patch and send that to the server. So it allows us to do things like slow down the sync on over wireless networks. Don't sync until the user takes an action, but then augment that with some sort of time-based, because if we're not running the loop, we're not getting changes from the server. So it gives us this extra level of indirection where we can control how often data moves from the client and server, how big the patches are, how responsive the user interface is based on the needs of our application. I think that's a pretty cool advantage of this technology. So I want to push a little bit into some of the more advanced things that we're looking at doing. This stuff is probably not going to be available in a first release of this, but it's going to give you an idea of where we're headed, some of the interesting things that you can do with this, maybe that you couldn't do with typical REST. I'll switch over and do a quick demo. Once you have a system of patches and the payloads are small, you can sort of think about streaming those out to a client over WebSocket. You could think about streaming them in both directions, in fact. I'm going to show one direction here. Did I kill that? Yeah, okay. This is actually an app that Craig wrote originally. I got my hands on it. I hacked it up. Good old Chrome caching. All right, so this is like, obviously, American football scores. Let's see how big I can make this. And I'm just going to let it sit on the screen while I talk about it for a minute. The server is generating, I'm going to reload. You know why? Because Chrome doesn't update its network panel unless you reload. The server has a stomp connection, is listening for stomp connections. The client has connected over stomp. So if I go to all here, I'm going to go to the very bottom of the network tab, and there's no puts, right? There's no additional gets, right? The server is, the client is not continuing to issue gets, right? I've just got a WebSocket open. This is a really great feature of Chrome's debugger. You can actually see WebSocket traffic. Okay, everybody see this? Everybody see a score updating here and there. It's kind of a slow process. But we're streaming changes from a Spring server that's running a Stomp endpoint out to a client that has a Stomp connection back to that server. So we're not powering up the radio multiple times, streaming it. We're not issuing multiple requests. We've just got the connection open. And I want to show you real quick. This is really the only code I'm going to show. But I do want to show it because it literally took me 5 minutes to transform Craig's application and put this user interface on it. This is all the JavaScript. And part of the reason it's so small is I'm actually using Rave.js. If you came to John Hand's talk, you know that Rave is sort of zero config for client-side JavaScript. So this is it. There's no boilerplate, nothing else. It's just a single function that runs my application. I installed some packages using Bower, a WebSocket package, and sock.js. And I just create a Stomp connection attached to a WebSocket that points at the server's Stomp endpoint. I connect. I subscribe to two destinations. One is going to give me the initial set of scores so that I can present that to the user quickly. The other one is a topic that's going to be broadcasting only differences, right? Only deltas using JSON Patch over Stomp. So when I get the first batch of all the scores, I'm just going to assign that to a JavaScript property. That's all I do. And then when I get updates, I'm using jiff just to patch that property, right? It turns out it's an array. It's an array of objects, and all I have to do is apply the patch to it. Anybody notice anything about this? Where am I changing the DOM? Right? Nowhere. This algorithm is being applied to keep the DOM in sync with this games property. I'll show you that now. Let's see. Oh my gosh. So there's the HTML. And the incubator library that I was telling you about contains this algorithm for diffing and patching the DOM as well. And all you have to do is sort of put some very simple landmarks into your HTML, and it will keep it in sync with JavaScript data. So pretty simple, very little JavaScript to make this happen, taking advantage of the fact that all I need to do is patch some data. Okay, that was neat. I've got another demo. Oh, algebra, that's a dangerous word. It turns out that there's a whole set of algebra for patches. All right, you all use Git. How many of you have used Git rebase? Raise your hand. Okay. How many of you, before you used Git, say you used SVN, ever heard of this thing called rebasing? Really? Great. Okay, cool. How many of you heard of patch algebra? Okay, you've all been using patch algebra. So behind the stuff that Git does to make your life easy when you rebase on someone else's changes is all based on a set of math called patch algebra. And when you rebase, the reason you rebase is, right, say Craig and I are working on the same repository. We both pull that repository, right? We have the same commit hash. We both start changing the files, right? Somebody is going to win the race to push their code first, right? Craig wins. He pushes his code. I've still got the old commit hash, and I have changes. Now, my changes have diverged from the copy that's in, say, the repo is on GitHub, right? Diverged from the remote, right? I can't, you know what happens, right, when I try to push my changes, right? Git yells at you, right? It says you can't do that. The remote has changed. And so what do? You fetch, and then you rebase. And that process of fetching and then rebasing is actually taking patches and rearranging them and changing them at the same time so that they can be applied out of order, right? My changes happened in parallel with Craig's changes. Rebasing stacks them like this, modifies them in a way that allows them to work out of order. So now we have a system based on patches. So we can do the same thing. One of those bits of algebra that's involved in that process is called inverse. Right? This is the simplest thing you can imagine. Right? You take a text document, you modify it, you apply a patch to it, you get a modified document. If you invert that patch and you apply it to the second document, you get the first document. Very intuitive. Right? This has a direct correlation with something we do all the time for our users. Right? We provide undo. So if we're changing the data using patches and we can invert those patches, we can very easily provide a very generic undo function. Not only that, we can provide the redo function by using the original patch or inverting the one we inverted already. So you can get this nice flow back and forth in time, right, for structured data. Pretty cool. And again, just like Git, we can actually do apply this notion of rebasing and the algebra behind it to allow people to change things in parallel and run the diff sync algorithm in a way that both end up with the correct copy of the data in the end. Our library, jiff, does support both of these operations. There's just a function, rebase. You give it some parameters, and it will do the magic of transforming these patches so that they can be applied out of order. One more demo. Just a very simple demo of some of this patch algebra. Okay. This is not going to be nearly as pretty, but it is functional. Okay, so very ugly to-dos app here. All right, works. Can add some to-dos. If I reload, it sticks. Okay, cool. The other to-dos app had an add button and a complete all and a remove completed buttons. They were little icons. This one has two new buttons, previous and next. You can probably guess what those are going to do. Let's add another to-do. Oh, let's undo that. Okay, cool. Let's redo that. Okay, that's kind of cool. Let's go back in time. Let's go forward in time. So you can sort of move around, right, in the history of your data. Now, obviously, you have to be keeping these patches around to do that, and you'd want to limit it to, you know, a certain amount of patches. But you can do some really interesting things. So, for example, there's where we ended up, right? Let's back up a little bit. Let's add another to-do, and let's go forward again. Oh, it still works. So that's actually rebasing patches out of order behind the scenes to make it all work out. And right, I ended up with something that was still intuitive. Let's start deleting stuff. Let's go all the way back in time to where I started. And go all the way forward in time, once again, and end up right at the end one more time. So it's pretty cool stuff. We're not exactly sure what all we're going to do with it, but now that we have this capability, you know, it's really interesting to think about what could we do with this, right? What kinds of things could we provide for our users? What kinds of things could we do on servers? What kinds of things can we do in clients with this kind of technology? So like Craig said, it is new technology. So we do face some challenges. And Craig mentioned a few of them that he's already fought the battle on. And there are definitely a few more that we have to get through. Originally, diffing and patching algorithms and patch algebra were really applied to document-based things, right? Text documents, right? The collaborative text editor is the classic example. But we're talking about structured data in a world where we deal with resources, entities, Java objects. So how do we make that translation between those two, right? How do we not shoot ourselves in the foot in an entity-based world using algorithms, you know, by transferring them from the world of document space to the world of entity space. There's this whole notion of the shadow copy. I'm not going to lie, it's very much a challenge. You can imagine if you have a server with, you know, lots of data, lots of users, maintaining a complete copy of each user's, an extra complete copy of all each user's data in memory is not feasible, right? There's got to be a solution here where we can be more efficient with this shadow copy and the differencing algorithm. Lists and arrays are tricky. Craig already talked about why. It's not only tricky in the Java world, it's also tricky in the JavaScript world for various reasons. And the biggie, the 800-pound gorilla in the room, is conflict resolution. However, we do have this hypothesis, and this hypothesis is that conflicts are created by user behavior, right? When the user uses your application in a certain way, they are more or less likely to create conflicts in your data. And we have this now, right? We have the @version field in our entities, right, for a reason, right, to prevent incorrect changes, changes being applied to incorrect version of the data. So really, conflicts are driven from user behavior most of the time. And we're not changing user behavior, right? The users are still going to use the system in the same way. So our hypothesis is that we're no more likely to create conflicts by using this technology because we're not changing user behavior. And where we're at today, the Spring Sync project, there's a build snapshot available. Like Craig said, the source code is available for you to try out. We'd love to get feedback. Contributions also very welcome. We have a released library called jiff for the JavaScript side that handles diffing and patching, has some of the fun experimental features that you can also play with. And we have this application that I showed is available for you to play with as well. And we're going to keep moving forward. We think this is really exciting, interesting technology that allows us to do things that we weren't able to do before. And we think it can provide real benefit to developers and to users. So we're going to keep moving forward with Spring Sync and the JavaScript side of the Differential Sync implementations. We're going to look at other ways that we can integrate this into the Spring ecosystem. You saw the Stomp demo, right? All the other demos were based on HTTP. How can we integrate this into a messaging environment? Can we integrate what's called smart patching based on these patch algebras into the server side to make it more resilient to parallel changes by multiple users? We want to tackle offline and disconnected support. And like I said in the beginning, the algorithm really lends itself to this very easily. All you have to do is just buffer patches on a client until you get the network back, right? If you're using a web browser, you can keep them in local storage. If you're using them on iOS or Android, you can use any one of the local storage options, native options on those platforms. So having very easy to enable offline support for developers to provide that to their customers is a cool feature that we're going to tackle. And then, of course, this is not a panacea, right? This is not start using Differential Sync instead of everything else you've been doing. This is an option, right? This is another tool in your toolbox, right, to provide great applications to your users, right? You shouldn't think to yourself that you're going to go out and replace your entire REST API with differential synchronization because it may not make sense for your application, right? You may be able to apply it over here, or you may have an application where it makes sense to apply it on a large scale, or you may only use it in one specific spot, but it's another tool in your toolbox. And because of that, we want to learn about what are the use cases where this is most effective, and how can we provide guidance to Spring developers to help them make the decisions about when to apply it, when not to apply it, and examples of how to apply it. So that's going to be a big part of this as well. And that's it. Thank you very much. Questions?
Yeah, a couple of questions. You've got the shadow copy. That is more of an observation
Mm-hmm.
But you have to sort of keep track of whether the stock version is on it. You have a shadow copy, you can look at that. But my question is, what advantage do you see of using this locally within the browser to update the DOM? That seems kind of overkill to me, but I'm sure I'm missing something.
Right. The advantage really is the programming model that it provides. Let me go back to the code. That's not readable, is it? Yeah. Okay. The advantage really is programming model. We're seeing a trend in the JavaScript world to get away from direct DOM manipulation. It's very error-prone. It's also a source of maintenance, right? Whenever you've written JavaScript that directly references aspects of the DOM, if the DOM changes, and you may have designers who are in charge of the HTML, right? Those things can get out of sync pretty easily, so it creates sort of dual maintenance. But if we can minimize that, we don't actually get rid of it entirely, but if we can minimize that and give a programming model where JavaScript engineers can deal with JavaScript, we think there's a big advantage there. And I mean, I think the proof is in the code here, right? All I had to do was just write JavaScript and put a couple of landmarks in my HTML. And this is the Scores app that you saw that was streaming from WebSockets. So we think there's real advantage in terms of programming model. Yeah, yeah, yeah. Angular's, yeah, that's a good question. Yeah.
One other observation or question. You talked about the offline disconnect time support, which is an interesting problem you're trying to solve.
Mm-hmm.
Have you thought about whether it makes sense to just, when you get time to do that, do the rebates and apply the patches there, or does that not make sense?
The question was, when we have disconnected clients and they come back online, can we apply the rebase algorithm to solve that situation where the client needs to reconcile? That might be possible. I haven't tried it, to be honest with you. The paper, the way it's described in the paper, is that you continue to track changes while you're offline. And so you buffer patches on the client. And there's some extra, very small amount of extra bookkeeping you have to do, which is basically you keep a version number of the latest copy of what you think you got from this, what copy of the data you think you have from the server. And there's this very simple reconciliation process based on version numbers that happens. And then the client and server can start exchanging patches again. So that's how it's described in the paper. I've not tried applying the rebase algorithm in that, but it may be a good solution. Other questions, please? Yes?
You may have mentioned it just a second ago when we were talking about this, but here with Angular, you would just be applying the patches in scope, right? It would accomplish the same goal. Right? You're not manually updating the DOM. You're updating the JSON that already been uploaded.
Yeah, the question was related again to Angular. Could you, I think you're getting at, how would you do this kind of thing in Angular, or could you do this kind of thing in Angular? Yeah, this is a very similar model to what Angular uses. We are doing some things that are a little bit different. There's the Angular dirty checking is what they call it, dirty checking loop. Is not based on a patch system. So we think there are some interesting opportunities here, around that. But in effect, right, they work similarly. Other questions? Okay, great. Thank you very much.